All right. Second order linear differential equations. Now, this is going to be a review of all the stuff that we have learned over in a specific chapter in the textbook that I'm using and studying for differential equations. And this is also a review for a test that I have coming up on Wednesday. I have 3 tests at that day. All right, so let's get started. So we wish to solve equations of the form ay double prime plus by prime plus cy is equivalent to some arbitrary function of f. All right. Now, a, b, and y can be variables such that a, b, and y can be functions of t, but it cannot be functions of y because that would not make it linear. Now, what we're going to do is we're going to dumb this down to the simplest case in which f of t is just equivalent to 0. Can y'all see that? I need to make this bigger. So, all right, where a, b, and c are both real numbers, and a is not equal to 0, or else that would just make it a first order linear differential equation, which can be easily solved using separation of variables. Now, this is what we call a homogeneous second order linear differential equation, all right? Also just call it homogeneous, right? Now, what we'd like to do for homogeneous equations, it's homogeneous because there is a 0 over here for the factor in the right side of the equation. We want to let y equal e to some power of rt. Now, we differentiate this like 2 times to get y prime is equivalent to re to the rt. And then y double prime is equivalent to r squared e to the rt. Now, if we plug these values in, we are going to get, for this homogeneous equation, a r squared e to the rt plus br e to the rt plus c e to the rt equals 0. Now, what we can do is we can factor e to the rt and get ar squared plus br plus c equals 0. Now, e to the rt is never going to reach 0, so we don't have to worry about this factor over here. Now, we need to only factor this part of the equation. Now, this is what we call the auxiliary equation. The auxiliary equation is mainly used in order to find root for specific parts of the homogeneous equation, and it's mainly used for in cases in which this equation over here, the original equation, is not homogeneous. So this is an important equation that we use, and this is how we derived it. Now, so we have the homogeneous equation, and based on that, we said that our solution was of the form e to the rt, and we have a quadratic equation of the form ar squared plus br plus c is equivalent to 0. Now, we know from high school that using the quadratic formula, r is equivalent to negative b over 2a plus or minus the discriminant b squared minus 4ac all over 2a, which implies that there can be 2 solutions to the equation. So we get that, let's say R1 and R2 are solutions of this. Suppose that. So which implies that y is equivalent to e to the R1t or e to the R2t. Now, the actual solution of ay double prime plus by prime plus cy, the actual general solution to that homogeneous equation, which is equal to 0, we call it a linear combination of all the possible solutions of y. Now, what does that mean? We mean that the actual general solution is just ce to the R1t plus c1e to the R1t plus c2e to the R2t. All right? Now, this is the general equation that we get. And then given any arbitrary constants a, b, and c, and then if we get initial values, we can solve for the equation, and then we can differentiate to find the constants. Right? So there are a wide variety of cases in which this can, not a wide variety of cases, there are just a wide variety of like different looking solutions. The first that we're going to consider is just a normal solution in which this only produces two distinct solutions. Now, if this contains two specific solutions, so y is just going to be equal to, the general solution is going to be a linear combination of e to the RT and e to the 2RT. Now, suppose that the actual solution to the auxiliary equation is a complex root. Now, I'm not going to go over to the main proof of this, but using Euler's identity and using the fact that the real and imaginary parts of a complex number are linearly independent of each other, because if you draw them as a vector, their components don't influence each other, we get that if r is equivalent to some form of alpha plus or minus I beta, in which alpha is just equivalent to this, and then beta is equivalent to this, assuming that the discriminant is less than 0, or the things inside here is less than 0. All right. If this holds true, then the solution set that we are going to get is e to the alpha t times cosine of beta t, and we get the other one is e to the alpha t sine beta t. This is the solution set for scenarios in which the solution sets to the auxiliary equation are complex. Now, I guess I should draw this on the board. Is it? No. So complex roots. Now, there are certain scenarios in, for example, in the case in which there are some quadratic functions in which only the function touches a specific part of the x-axis, which implies that there are double roots. So this is the case in which b squared minus 4ac is just equivalent to 0. Now, for the case of double roots, we can't just have only one solution being ce to the RT, because there are the function, the differential equation is second order, which implies that there are two constants, because if you differentiate once, you get an initial constant c, and then if you differentiate, if you integrate again, you get another constant c. What we're going to do is we're going to smack a t right over here. So the solution set for any double root equations It's just going to be the set containing e to the RT and then TE to the RT. This is done in order to maintain the linear independence of the solution set of the homogeneous differential equation. So to summarize, for all equations of the form ay double prime plus by prime plus cy is equal to 0, with auxiliary equation ar squared plus br plus c equals 0. If r is a complex number, we get the homogeneous set just equivalent to e alpha t alpha t, and if r has two roots, or the auxiliary equation has two solutions, we just get the set of the solutions, the homogeneous equation being equivalent to e to the r1t, e to the r2t. And for double roots, so basically r is equivalent to negative b over 2a, such that b squared minus 4ac equals 0, the one that has the plus minus, we get that the set is just e to the RT, TE to the RT. Right? Now we are going to discuss the method of undetermined coefficients, which is a method of finding particular solutions for the non-homogeneous equation a y double prime plus b y prime plus c y equals f of t. The first thing that we are going to do is we are going to consider f of t is equal to ct times e to rt. Ct to the power of m times e to the power of rt. Now, if the non-homogeneity is equivalent to this, we are going to set the particular solution be equivalent to t to the power of s times a t times t to the power of m, or any arbitrary polynomial to the power with a leading degree m. So we're going to continue this down with decreasing polynomial degrees until we get to 0. So m minus 1 plus 2a naught times e to the rt. All right. Or actually, we're going to have to put a constant here. So not c, let's just say b. All right, so we have to solve for b, and then each coefficient in the arbitrary polynomial depending on m. So for example, if f of t, so if f was equivalent to, let's say, 2t times e to the 4t, we're going to say that y sub p is equivalent to a1t plus a naught. We're going to put a constant over here, so b, and then times e to the 4t. Notice that I did not put an s on t to the power of s, so I'm just going to put t to the power of s. Now, you may be asking, why do I have a t to the power of s? Now, s, we do this in order to, actually, another way to form it. This as a factor actually depends whether the roots of the auxiliary homogeneous equation. So remember that the homogeneous equation was of the form AR squared plus BR plus C equals 0. Now, if we said that f of t was equivalent to ct to the m times e to the power of rt, I did not put that r in there for no reason, right? So if the associated auxiliary equation to the differential equation, if the roots of that auxiliary equation match those to r, to the constant or the non-homogeneity constant located in e to the rt, so this constant right here, all right, so basically this is a solution, one of them is a solution. We have to consider a wide variety of cases. So if one of the roots, at least if one of them, only one of them, of the roots of the auxiliary equation match those with e to the rt, would match those with the constant multiplied by t in e, then we have to multiply by t. So we get the particular solution be equivalent to t times a sub m times a sub m times t to the m plus go on until you get a constant times e to the rt. All right, this is only for one root. Now, suppose that if the auxiliary equation has double roots, so remember in our last discussion, double roots, remember what we did for homogeneous equations, we multiplied the second solution by t. We kind of do the same thing, but we already use t. So what we're going to do is we are going to set the particular solution to be equivalent to t squared times the arbitrary polynomial a sub m times t to the power of m plus a sub m minus 1 times t to the power of n minus 1, and so on until we get a naught times e to the rt. All right? Now, this was for real roots to the auxiliary equation. Now, if we, this is, to summarize, this is only if it matches, right? In which you have to multiply it. If it doesn't match, then you just get a t m plus whatever, the arbitrary polynomial times e to the rt. So this is your particular solution. Now, if your homogeneous equation is of the form, so it's going to be of the form e to the r alpha t, so f of t is equivalent to e to the alpha t, and then times cosine of beta t, or this can be sine of beta t. What we are going to do is we're going to set the particular solution be equivalent to all right, we are going to talk about a extremely useful principle for solving second order linear differential equations or for any higher order linear differential equations, and that is called the superposition principle. Actually, this is a review, by the way, so I'm just going to review this slightly, assuming that you have read the content and you just want a refresher. So for ay double prime plus by prime plus cy is equivalent to an arbitrary function of t plus another arbitrary function g of t. What we're going to do is we are going to split this equation up into two. So we're going to split this based on ay double prime plus by prime plus cy is equivalent to f of t, and then we're going, by that sense, we're going to find a particular solution for just this equation over here. Can you see that? Hopefully. All right. And then, so basically we find y sub p1, And then after that, we found y sub p1. We then find the particular solution of ay double prime plus by prime plus cy is equivalent to g of t. So y sub p2 for this solution. All right. Now, after we have found those two particular solutions for this differential equation, we're going to see that the total particular solution, so the particular solution of this differential right here is just going to be the particular solution for solving this equation, but only equals to f of t. So I'm going to write it right there, plus the particular solution for when solving for g of t as the non-homogeneity. Now, if you recall from our first part in solving homogeneous equations, we said that ay double prime plus by prime plus cy is equal to 0. But technically speaking, aren't we actually adding 0 here? Now, by the superposition principle, okay, now actually before we get to superposition, we have found a general solution and an actual solution given the initial values if we found the homogeneous solution set of only this equation only. And then if we use the superposition principle, we are going to get that the general solution, i.e. we have the constants right there and we need to solve for the constants, the C1 and C2 for the homogeneous equation. The general solution of any non-homogeneous second order linear differential equation, assuming constant coefficients, I think this may apply to variable coefficients. All right, this is going to be equivalent to the particular solution, so all of the particular solutions adding plus cy1 plus cy2. So y1 and y2 are the in which y1 and y2 are both the homogeneous solutions of the associated homogeneous equation of the second order linear differential equation. Jeez, that was. Now, there is a faster way of finding a particular solution to the non-homogeneous second order linear differential equation, a y double prime plus by prime plus cy equals f of t. And so what we are going to do is, the first thing that we're going to do is we're going to find the homogeneous solution. So the two solutions to ay double prime plus by prime plus cy equals 0. So suppose that the solution set of this is y1 equal just s equals of the homogeneous y1 and y2. Then what we are going to say is our particular solution is going to be of the form v1 y1. So v1 times y1 plus v2 y2. This is going to be our particular solution. And then we are going to differentiate this 2 times, and then we're going to plug back into the equation. And then after we do that, we are going to get, remember we're still solving for a non-homogeneous equation. What we're going to get is that we're going to get a system of linear equations that says v1 y1, v1 prime y1 plus v2 prime y2. No, v2 prime y2 is equivalent to 0 because of a restriction that we placed inside this function. This is the restriction that we made. And we are going to get that v1 prime y1 prime plus v2 prime y2 prime is equivalent to f of t, the non-homogeneity, divided by the leading coefficient over here. All right. Now, if you know a little bit of linear algebra, all right, we're going to get that v1 prime is equivalent to the determinant of 0 f divided by a, y2 and a y2 prime divided by the Wronskian of y1 and y2. Now, the Wronskian is a determinant, i.e. the Wronskian of y1 and y2 for the two case is just equivalent to the first row you have y1 and y2, and then in the second row you take its derivative, so y1 prime and then y2 prime. All right. Now, if you know linear algebra, some stuff from linear algebra, and recall from what we said about the solution set of the homogeneous equation being linearly independent, what this implies is that this determinant right here, if we did the math right for solving the homogeneous solutions y1 and y2, it means that this determinant right here is never going to be 0. So we can assure ourselves that this is always going to work, assuming that we did our arithmetic correct and we found the solution for the homogeneous equations. All right. Similarly for V2, this is going to be equivalent to y1 and then y1 prime. So this is the determinant, and then 0, and then f divided by a divided by the Wronskian of y1 and y2. All right. Now, if you can't remember this equation, you can always go back to the original system, v1 prime y1, no, v1 prime y1 plus v2 prime y2 equals 0, and v1 prime y1 prime plus v2 prime y2 prime is equivalent to f over a, and you can solve it yourself. All right. Remember that this is still prime, so in order to get rid of the prime, we have to integrate this entire thing in order to get the particular solution of the equation. All right, and once you have found a particular solution to the non-homogeneous second order linear differential equation, now we can actually find a general solution by recall what I said about the superposition principle, that the general solution, so the actual solution is cy1 plus cy2. So this is the homogeneous solution plus the particular solution that we have found using the variation of parameters method. That is a mouthful. Sorry, my phone ran out of battery. All right. Anyways, where were we? All right. Cauchy-Euler equations. So we have learned that the associated auxiliary equation was nothing but AR squared plus B minus A times R plus C is equivalent to 0. And that was done by setting y equivalent to t to the power of r. Now we have to deal with three scenarios for the Cauchy-Euler equidimensional equations, and that has to do with the solutions and the type of number that r is. Now, if r has two distinct real roots, and that means that the solution set, so two real roots, all right, we get that the solution set is just going to be, and the general solution for the homogeneous Cauchy-Euler dimensional equation is going to be a linear combination of t to the power of r1 and then t to the power of r2, where r1 and r2 both satisfy this quadratic equation. Now, if r is a double, and if the associated auxiliary equation is a double root, meaning that the graph of this touches the x-axis once, so double real roots, we get that the solution set is equivalent to t to the power of 4. And remember what we did for the previous scenario in the associated auxiliary equation for the constant variable second order linear homogeneous equation. We just marked a t in front of that e to the power of rt. We're going to do the same, but we are going to multiply by log of t. So it's the second solution is going to be t to the power of 4 times log of t. Right? Now, if your solution set to the quadratic equation is going to be complex, we are going to get the s, the solution set to the associated auxiliary equation is going to be equivalent to, remember that what we did for the homogeneous equation, it was equivalent to e to the power of alpha t cosine t beta t times e to the power of rt times sine of beta t. Now we're going to do the same here, but it is going to be so t to the power of alpha times cosine of beta log t, and t to the alpha sine of beta log t. Those are going to be your homogeneous solution set. For the equation a t squared y double prime plus b ty plus cy is equivalent to some arbitrary function of t, right? Now, in terms of actually solving for the non-homogeneous Cauchy-Euler equidimensional equation, that is actually hard to solve, so we are not going to focus on that.